Hey guys, I'm going to lecture through your topic 1.3 handout, and I'm recording it to YouTube for posterity. Excuse me. Okay, so in the first example, we are asked to find a third vector, a force vector, that will keep the system in equilibrium. And the way that we put a system into equilibrium is adding up all of the vectors such that their sum is equal to 0. Okay? So the way that we do that is demonstrated here, where we've added our initial vectors together, which I have identified as vector A and vector B. So the sum of vector A plus B will be equal to C. And in order to neutralize vector C and put the entire system into equilibrium, we need to add the opposite of C, the negative of C, to this system. So you can see that we have done that here with this guy. So there is our balancing vector, vector negative C. Okay, so there you go. There's our first problem. Second problem, we are given a velocity magnitude, a velocity vector with a magnitude and direction. We know that it's horizontal, and as you can see in my diagram here, I've assumed that it's horizontal and positive. So a second velocity vector has a magnitude of 2.0 meters per second, and that is going to be added to the first so that the sum, the resultant vector, is vertical. Okay, so find the direction of the second vector and the magnitude of the sum of the two vectors. So I think I forgot to do that second part actually. So I might come back to that later. We'll do it in class. In any case, so for number one here, we have our draw a diagram instruction. So this is what we want. We have a sum of vectors, A plus B, and we know that they will equal C. And based on the problem, we know that C must be vertical. So when I started setting this up, I start with vector A, it's horizontal, and I know that vector C, in order for, vector B, in order for vector C to be vertical, vector B is going to have to tilt backward, back toward vector A, and then the sum of the two will be equal to vector C, which here produces a nice right triangle. Okay, so hopefully this is all looking pretty good now. Next, we need some algebra and trigonometry, and that looks like this. So we know that bx plus ax is going to equal 0 because our resultant component has no horizontal vector. So vector C has 0 horizontal component. Okay, so that means the sum of our horizontal components must be equal to 0. And that tells us that vector b sub x, the horizontal component of b, is equal to the negative horizontal component of a sub x. And we have a value for that. Okay, so that value is negative 1.2 meters per second. Note that assigning minus signs becomes occasionally a little bit tricky, and so keep that in mind as we go forward. Okay, we also know that b sub x is equal to the magnitude of vector b times cosine of its angle, which I am calling here alpha. Okay, so that means that cosine of alpha, doing a little bit of algebra here, will be equal to b sub x divided by the magnitude of b. Okay, so we've divided both sides of this equation by b, and that gives us this relationship. And once we have that value, we can use the inverse cosine function to find our angle and plug in some numbers here. This is actually not exactly the angle that you would get out of your calculator, but it is rounded off to two significant figures, which is appropriate under these circumstances. although sig figs and trig functions present some interesting challenges. So be a little bit careful there. To find the magnitude of this vector, so we've got the radius, and the radius is 2, and we know the angle, so we just plug that into a cosine function, or a sine function. So if we know this angle 130, our magnitude of C is just going to be equal to the magnitude of C will be equal to 2.0 meters per second times the sine of 130 degrees. And I'm not going to plug that into my calculator right now because I'm in a hurry, but this will give you the magnitude of that vector. So the hypotenuse is 2.0 meters per second, the hypotenuse of this right triangle. And so we just need the sine function to find the magnitude of C. And since it is vertical, the magnitude is basically the defining characteristic. Okay, so there is 1.15, and I will beautify this a little bit before I share this document with students, or I should say it'll probably be updated as I go, which is slightly dangerous. Okay, anyway, moving on. Finally, 1.16. A person walks 5 kilometers east, followed by 3 kilometers north, and then another 4 kilometers east. Find their final position. You could do this with a ruler, or you could do it with graph paper. Either would be okay. And then what I recommend that you do is draw a diagram of the movement. And you will determine the final position then in terms of coordinates. So I've shown a diagram of that right here, where you can see we're moving 5 kilometers to the east, we're moving 3 kilometers to the north, and we're moving 4 kilometers again to the east, as instructed. I then have drawn this blue vector, and I've named this blue vector S. The reason I've named it that is because that is the vector name that we use for displacement, as you will see in topic 2. Okay, the important information that I can glean from this diagram, in particular though, is the coordinates of my final destination, which in terms of XY coordinates is 9.0 kilometers and 3.0 kilometers. Okay, next, we're asked to find the magnitude of the displacement vector, and it's not super clear that this is what we are supposed to do, but this is what we are going to do because we have the information and we should use it. Okay, so we will find the magnitude of the displacement vector S by using the Pythagorean theorem. We have our x coordinate and our y coordinate, so we just plug those in to the square root. So we square both of those and then take the square root of their sum, and that will give us 9.5 kilometers to 2 significant figures. Okay, so then we find the direction of the vector, and we do that using the tangent function, and that will give us 18 degrees. It's pretty straightforward. I don't think I need to dwell on it too much. Okay, note that when I'm plugging things into the tangent function, it's not really good use of time necessarily to add units that are just going to cancel out, or decimal places and zeros that aren't really helpful. So just for the sake of speed, you can kind of ignore the 2 significant figures that technically should be here. Okay, we still have quite a lot to go. Okay, so a body moves in a circle of radius 3.0 meters with a constant speed of 6 meters per second. So our velocity vector is at all times tangent to the circle, and that is actually the case for velocity vectors, as we will see in topic 6. So the body starts to A, proceeds to B, and then to C. Find the change in the velocity vector between A and B and between B and C. So we are going to diagram this change, and it's helpful to think about what changes in stuff look like, okay? So the way this works is you take your final value and you subtract from that final value your initial value, and this is how you calculate a change, can calculate a change in anything, pretty much. There are some exceptions to these rules, but mainly in thermodynamics, but there are good reasons for those. And we will talk about that more in topic 3. When I make videos for topic 3, we've already covered it in this course, actually, at this point. So anyway, what I've done here is set this, wait, no, we haven't covered it. Topic 3 is upcoming. This is topic 1. Okay, sorry. Anyway, the key point here is that we have vectors, and I'm changing this system so that instead of subtracting vectors, we are adding them. The reason I'm doing that is just because I just prefer to add vectors whenever possible. It makes a little more sense to me. It's a little more rational than the tail-to-tail method that you will see, ouch, in the book. So I've done it slightly differently than your book here. Okay, so when I diagram my vectors, it will look something like this. And note that we have tip, this is the tip, to tail. So I am adding my two vectors, VB and negative A. Okay, so I've just drawn negative A here in the opposite direction as my original vector, and that's how that works. Okay, and I have values for both of these, and they're negative 6.0 meters per second and negative 6.0 meters per second. They are both negative, and these are due to the Cartesian coordinate plane conventions, okay, where down is negative and left is also negative, where also up is positive and right is positive. So it can be helpful to think of these coordinates when you are dealing with vectors. It's going to make your life a little bit easier. Okay, I can now find my magnitude for this vector by using the Pythagorean Theorem. And the nice thing about this is it will also be the magnitude of my other problem. Okay, so I find the magnitude using the Pythagorean Theorem, and I get 8.5 meters per second. We then look at direction, and this is where things get slightly trickier. Okay, I have to add 180 degrees to my arctangent value. And the reason for this is because if I just plug this into my calculator, what happens is my negative symbols cancel each other out. And that instead of ending up in quadrant 3, which is where I want to be, here, I will end up in quadrant 1. And that is not where I want to be for this particular vector. So in order to get my vector in the right quadrant, I have to add 180 degrees. This does require a little bit of thought, and it's one of those cases where having a diagram around is going to help a lot, because it's very obvious from this diagram that I am in my third quadrant, okay, which should be mathematics review for all physics students in theory, okay? So from this point, everything is very straightforward. And in fact, you could do this without using your calculator at all. If you just know that this is an equilateral triangle, then you know that this guy here is going to be 45 degrees, okay? Immediately. You just know that from your previous math classes. Okay, so when we look at B to C, we go through the same process, and I'm going to kind of move along here. The only major difference here is that I now have a positive vector because my initial vector for point B is pointed downward. So if I'm taking the negative value of B, that's going to point upward. But again, we're just using simple vector addition, tip to tail, which you guys should be very familiar with by the end of this topic. Okay, my direction, again, if I just plug this directly into my calculator, it's going to give me an angle that doesn't match the angle of this vector. It's going to put my vector in quadrant 4. And this is just the nature of trigonometry, so hopefully this is not new for you. If it is, play around with some example problems and kind of work through what's happening. But if you have any questions, don't hesitate to ask. We can go through it in a little more detail and with more examples. All right, so anyway, I plug in my values and I'm going to get 135 degrees. Again, another equilateral triangle, so I know that those angles are going to be, the non-90 degree angles are going to be 45 degrees, okay? All right, 1.18, find the components of the vectors in figure 1.21. This should be fairly clear, but let me point out that your angles, the only thing that is perhaps not clear is this. Your angles should generally be measured from the x-axis pointed toward the right. Okay, so this is the convention that is just always the case. Okay, so if you're given these values, we have to make some changes quickly to make this all work out in your calculator. Okay, so for A, I probably used alpha over there. I did. Good job, me. Okay, so alpha is going to be equal to 180 plus 45, which is 225 degrees. Okay, 30 here. We could go all the way around and call this 330. We could do that, or we could just call it negative 30 degrees, and we're still measuring then off that horizontal x-axis pointed to the right. So that works. Okay, anyway, you can pause here and take a look at this. I don't think there's much point in explaining it all. It's all just set up as you would expect. Again, these formulae here are straight out of your data booklet. And in the case of the b sub x and b sub y, I did not actually write out the formula because I think we should all be able to figure it out from here. Okay, so if you get stuck, let me know. All right, next one. Draw the components of vector w along the axes shown. So, first step is to draw a diagram, and this is frequently the case. So, I've just drawn, so here's w right here, and then I've drawn our component vectors along the axes as instructed. Okay, note that my vector here is not perfectly lined up, a little bit sloppy. You can't really see it when it's zoomed out, but anyway, there you go. It's supposed to be on that axis. Okay, so in addition to drawing these vectors, I've given them names, and we will see why these names make sense in a little more detail in topic 2. But basically here, this F is our net force on an object we would place on this ramp. And negative R here is our negative normal force. Again, I will explain that in more detail later. For right now, just don't worry about it. You can give them whatever name you want. Okay, so what we have here, ta-da, is another right-angled triangle, which means that we're going to be defining our component vectors using cosine functions. So, the magnitude of our component vectors, the magnitude of our vectors will be given by W. Okay, so this would be the hypotenuse of a right triangle. And I've written some text here. You may want to pause and take a look at it. But once we have a right triangle, then we are good to go on our sine and cosine functions. Now, you may be asking yourself, how do I know which to use? The answer to that question is pretty simple. You may need to, however, rotate your diagram or your paper to see what we should do here. But basically, this angle, theta, will always be measured against the adjacent, okay? So you remember SOHCAHTOA, right? Opposite, adjacent, hypotenuse, etc. So our angle is always measured against the adjacent, and again, that's given by the cosine function. The opposite then will be given by the sine function. So there you go. This is should be review for you guys, but this is really common. It's really common to reverse these and mess it up, and that's going to cost you a mark or two if you do that on an exam. Okay, our last bit here, yep, this is it. Find the sum of the vectors shown in figure 1.27. I will break down vector addition in a little more detail in another video, I think, and show you some techniques that you can apply. But basically, I have set this up, and this is going to be a pretty quick and dirty one. So don't. If you find this a little bit confusing still, don't get too worried. I will break it down further later. All right, but anyway, to start, let f sub 1 plus f sub 2 equals e. The reason why I have done this is because, as you will see below, when we're talking about the components, it's just a lot more clear if we define that sum as another vector. Okay, so we then calculate the horizontal and vertical components by vector addition. So the horizontal component of E is going to be equal to the horizontal component of f sub 1 plus the horizontal component of f sub 2. Okay, and we know from our data booklet that that will be given by the magnitude of the vector times the angle of the vector. As you can see, we have a little bit of a problem here, and that this 42 degrees is not measured against the horizontal axis pointed to the right. Okay, so to find the actual angle we need for our cosine and sine function there, we need to subtract 42 degrees from 180, which is what I've done here. Okay, then to that horizontal component that we've just calculated here, we need to add the horizontal component of the other vector, and this is a little more straightforward because that 28 degrees is measured directly from the horizontal Cartesian coordinate plane, the x-axis pointed to the right. Okay, so that's a little easier. And when we do our math in our calculator, this could be two operations, it could be one operation as I've shown here. You know, if you want to break this down so you're calculating the horizontal components separately, it's not a bad idea. In fact, I kind of recommend that you do that because you can pick up marks where you might lose some marks if you do too much stuff at once. Anyway, when we complete this calculation, we will find that our horizontal component is 4.7 units. You should have the unit here, okay? So just 4.7 is not acceptable. Just 11 is not acceptable. In this case, our unit is units, okay? So you'll note that I've left those units in the equation. It might seem silly, but later, trust me, it will be very handy to have the units in your math. Okay, once we have these horizontal and vertical components, we can find magnitude and direction. And we do that using the Pythagorean Theorem for magnitude. And we will find that our magnitude is 12 units. We have two significant figures. Okay, our direction, which I have called theta in this example, is given by arctangent of the y component divided by the x component. And that will give us 67 degrees. So a good idea, guys, is to do a quick sanity check to see if this all makes sense. So what do I mean by that? Well, let's take a look at f sub 2 here. F sub 2 has a magnitude of 12 units, and we've just calculated that our new vector also has a magnitude of 12 units. So do these, excuse me, do these two vectors appear to be about the same length? Yes. Okay, that's good. That's an instant check. If I had a magnitude of like 47 for vector E, that would probably indicate that I had made a mistake. Okay, so because they both have a magnitude of approximately 12, that's a good indicator that we're on the right track with our mathematics here. Another good indicator is to look at the angle, 67 degrees. And when we look at E here, and we look particularly at theta, does this appear to be about 67 degrees? Yeah, I mean, that seems like a pretty, I don't have a protractor in front of me, but it's greater than 45 degrees, right? It's less than 90 degrees, right? So I can do a very quick sanity check there, and it looks like my angle is on point, and I can check it without any special powers or magic. I'm just using logical inference, and that is a superpower in this course. Okay, guys, I will have shared this PDF with you and probably made one or two minor updates. And if you have any questions, do not hesitate to ask. This is a very, very important subtopic, and you need to have a handle on it because vectors will reappear and reappear and reappear. And if you are not very comfortable with them, it is going to be harmful to your progress in physics. So get comfortable now. All right, have a great day.